the segment for the Q&A part for the synchronous talk. As before, if you have any question for the panelists, write them using the Q&A button. And okay, I would, and please indicate the speaker they are directed to. So I would first ask all the panelists to introduce themselves and to give us like a 1-2 minutes summary of the main points of their talk. And we can follow the order in the slide. So Anirban, if you would like to go first, please introduce yourself.
Yeah, sure. Hi, everyone. I'm Anirban Das. I'm a postdoc at SLAC. I talked about self-interacting neutrinos as a solution to the Hubble tension with a question mark. So to give you a brief summary, I first described the cosmology of self-interacting neutrino, how it affects the TMB power spectrum. It creates an enhancement and a phase shift to the spectrum, and how previous works, people have tried to use that to solve or address the Hubble tension. And then there are many laboratory experimental constraints on flavor universal neutrino self-interactions, which have been considered in previous works. So that motivates us to look for flavor-specific or flavor-dependent neutrino self-interactions. And that was our work, and I described how things change in a flavor-specific scenario, and what's the relation with the Hubble tension for that. So yeah, that's it.
Thank you. Jeffrey?
Hi, I'm Jeff Hyde, and I talked about, I guess, building off very nicely on what Anirban was just talking about, flavor-specific neutrino self-interactions and how those would show up in astrophysical spectra. So we looked at a couple of examples, the diffuse supernova neutrino background at Super K and high-energy astrophysical neutrinos at IceCube. And on top of that, we developed a more efficient way of calculating the effect of these flavor-specific self-interactions on spectra rather than just running a big Monte Carlo.
Thank you, Jeffrey. Maria Cristina?
Hello to everybody. I'm Cristina Volpe, working at the Astroparticle and Cosmology Laboratory in Paris. My talk is on neutrinos from Kokolek supernovae, in particular flavor mechanisms and future observations. And I wanted to highlight recent progress in this complex domain, and in particular discussing the presence of multiple MSW resonances, slow and fast modes, and the implications for observations, in particular for the eagerly awaited detection of the diffuse supernova neutrino background that is just upcoming. Thank you.
Thank you. Raymond?
Yes. Hi, my name is Raymond. I'm a postdoc at the University of Minnesota. My talk was based on the recent progress on axion physics. In particular, we look at the unexplored dynamics of the axion in the early universe, which would be a rotation in the field space instead of the oscillation in the field space. And we found that this newly discovered dynamics can give rise to axion dark matter or dark photon dark matter, and also the baryon asymmetry that we observe in the universe. Simultaneously, we may be able to produce gravitational waves across the entire frequency spectrum that is observable. Thank you.
Thank you. Sergio?
Ciao, Nicola. Hello, everybody. So, well, I'm professor here at the University of Granada in Spain, and I prepared this talk on behalf of the Antares and KM3Net collaborations. So I belong to these two big infrastructures, and in my talk I try to give an overview on the physics program that we cover with these undersea neutrino telescopes. So I reported the main results that we already obtained with Antares, which has been taking data since 2008. So we have more than 13 years of data, and also try to give the perspectives. So the future for this kind of detectors, which is KM3net. We are all very excited because we already have 12, what we call 12 strings, 12 lines deployed. And the plan is that for the end of this year, we will double the number of strings. So we expect to have more competitive physics results in the future. So thanks.
Thank you. And Volodymyr?
Hello, and thank you for the organizers for the opportunity to give a talk. So my name is Vladimir Takistov. I'm a Kavli Fellow at Kavli IPMU, University of Tokyo, and I discuss primordial black holes. And this is right now a very exciting era for PBH because of multi-messenger astronomy. I presented some new scenarios of formation of black holes from scalar fields. One of them is from the so-called bubble multiverse, which gives generic broad spectrum of PBH, and perhaps this might have been already detected at the super hyper supreme cam. I have also discussed various exciting observables. If you have very tiny primordial black holes that make up dark matter that could interact with compact stars, such as neutron stars and white dwarfs, I have presented a new test of solar mass black holes, which are unexpected in conventional astrophysics, but perhaps could be primordial black holes or from dark matter interacting with neutron stars. I have also discussed a new idea how to test intermediate mass black holes, which have been definitively very recently detected, and through the gas heating. And the idea here is that a big black hole flying around in gas will deposit energy in gas through a variety of mechanisms, and one can compare cooling versus heating to constrain a wide parameter space. And finally, I introduced a new way how to use coincidence gravitational signals to test uncharted territory of evaporating very small primordial black holes. Thank you.
Okay, great. So we can go to the Q&A. So the first question is both for Anirban and Jeff, and I would like see what you think about this. So are there any current theoretical models that predict the neutrino self-interaction that you are considering? And can you constrain these models using some experiment on Earth? Terrestrial neutrino. Yeah, this self-coupling scenario. So I don't know, Anirban, if you want to go first, and then Jeff.
Yeah, sure. I mean, in general, I would say it's a bit difficult to write down neutrino interaction that does not affect any other charge leptons in the standard model because they belong to the same SU2 doublet. So, but there are some effective models where you can have some right-handed neutrinos and some heavy scalars at some high energy, and they create coupling between different flavors of neutrinos. And it's possible to suppress in those models. It's possible to suppress the interaction with the electrons or muons, for example. So there are a few examples, but not many. And about the question of what was the second part?
If there are any experiment using terrestrial neutrino that can probe these self-coupling models.
Oh, yeah, sure. There are several laboratory experiments. For example, one is if you have some new portal through, so let's say some new mediator phi and nu1 nu, there would be additional decay channels for example, 2 neutrino double beta decay or the decay channels of K mesons. So you can look for those new channels and you can put upper bounds on these new couplings. And that these are like the main avenues to constrain the flavor universal neutrino self-interaction that I talked about in my talk. And they put quite strong constraints on these kind of scenarios.
Thank you. Jeff, would you like to give us your opinion?
Yeah, that was a very nice answer. And just a little bit to add on to that, there are some constraints on the more flavor specific self-interaction, for example, from tau decays. But for something like a nu mu, or nu tau self-interaction, the constraints are relatively weak in terms of the coupling, and especially at higher mediator masses, they're weaker. So yeah, so just to add that.
Okay, thank you. So a question for Maria Cristina. So in your talk, you were saying that there are like great prospect to detect the diffuse supernova neutrino background, and you say that like the current sensitivity is just above the signal we expect. My question was about the uncertainties in this estimate, because I guess it depends from the star formation rate, which is something that which is something that we still don't understand really well, I think. So can you comment on that?
Sure. First of all, I want to say that the predictions by different groups show that we are not far from the experimental upper limit. Obviously, it depends on the star formation rate. And in the last but one slide, I was giving one of the several figures that exist. This is one recent by Priya Lunardini. And in fact, what you see there, the pink band, is including both the uncertainty on the on the co-collapse supernova rate, and also different possible contributions of what we call the failed supernovae. That is a supernova that turn into black holes, for which the fraction is subdominant compared to those that turn into neutron stars. But they do affect the spectrum of the relic neutrinos because they produce hotter fluxes, and therefore they modify the tail of the relic neutrinos. So to summarize, your comment is right, but this is indeed accounted for example, in this calculation. So, and the width of the band corresponds to a fiducial and an optimistic and a pessimistic case for the rate. And so you see that this gives you an idea of the fact that we are in principle close to the super K limit, even including this uncertainty.
Yeah, the band is really narrow. Okay, thank you. So a question for Raymond. So at a certain point, you're talking about this tachyonic instability that end up generating gravitational wave radiation. And you provide an estimate for the ratio of energy density in gravitational waves with respect to the energy density in radiation. And I was curious if you had any, if you compute any number of that quantity, and if you thought that this can have an impact on the number of relativistic species we can constrain using cosmology.
Thanks a lot for the question. Yeah, so there are actually a standard constraint on the number of species from the gravitational wave at this time of CMB. So if I remember correctly, that number is around 10 to the minus 6 in omega GWH square. So we are not offering any additional constraint from that. And in terms of the estimate of this gravitational wave strength, what is complicated is that tectonic instability is a process that's highly nonlinear, which means that the process is produced by some resonance, and the process is stopped because of the back reaction on the initial axion rotation. So we would not be able to analytically and very accurately determine the gravitational wave strength. So what we do is that we assume that when the gravitational wave energy, when the dark photon energy density is comparable to the axion energy density, then the back reaction becomes important. And that is consistent from different ways we estimated analytically. And it's also consistent with some of the lattice results using the axion oscillations. But remember, we're using axion rotation in the field space instead of oscillation. So the lattice simulation may not carry over completely, but that's a good estimate that we can make. And for that estimate, then we found that in the pretty much the entire gravitational wave parameter space, we're able to produce enough strength and at different frequencies with the model that we wrote down in the paper.
Cool, thank you. Mm-hmm. So a question for Sergio, which might be very basic, but I'm really curious. So I've seen from one of your first slides that ARCA and ORCA are kind of complementary. And I was wondering why that was the case, if it was just a matter of the volume that they cover, or if they were just sensitive to different energy density.
Yeah, you are right. So the idea was to have two different but complementary devices. One that is optimized to, let's say, low energies, and this is ORCA, and another one which is optimized to higher energies, which is ARCA. So we, in the case, for instance, in the case of IceCube, the model they followed is to have a big, very big device, so with strings spaced by long distances, and put a core detector inside, so something denser inside the big volume, in order to be sensitive to the low energy part in the core of the detector, and then to do astrophysics with the big volume. So in our case, we have two different devices at two different places. One which is very compact, which is ORCA, and which is more sensitive to neutrinos at the GeV, say hundreds of GeV. And then we have ARCA, which is less denser, more space between optical modules, which is more sensitive to energies up to the PeV. So the idea is to do somehow physics with the two devices, but to have the highest possible effective volume at low energy with one device, and at high energy with the other device. But in any case, we can do also physics with the two detectors at the same time. For instance, we just published a few weeks ago a paper on supernova detection using the data from the two devices. So it's not that one detector can only do low energy physics and the other one can only do high energy physics. The point is that one is specifically designed to be more efficient at low energies. And it's just a matter of how the optical modules are arranged. But the technology is exactly the same. So you have exactly the same volume, the same technology. So thanks for the question. I can't hear you.
Sorry, a question for Vladimir. In your talk, you were talking about these transmuted black holes, and you were saying that large mass candidate I think is larger than 1.5 solar masses, are unlikely to be transmuted. So, can you comment on why that is the case? So, is there something like some physical process that prevents these neutron stars to be transmuted into black holes, or?
Oh yeah, thank you very much for the question. Perhaps if you can show the slide that's
yeah, that's fine.
Yeah, so just a little bit of backstory. So in astrophysics, you do not expect the black holes below 2 solar masses, and this just comes from neutron star stability, the so-called Tolman-Oppenheimer-Volkoff stability limit. And so for a lot of people, they take detection of black holes below solar mass or around solar mass to be like some sign of PBH, a clear signature. But they also can appear, for example, if dark matter, either particle dark matter or a small PBH, interacts and eats a neutron star. So if a small PBH is either captured or particle dark matter accumulates, collapses, and then eats the neutron star. And recently, LIGO detected an very exciting candidate event that, if we do have population of such black holes, and the question is, well, how can you tell their origin? And this is, of course, very important astrophysical question. And the idea here is that a very simple test is that any kind of dark matter interacting with neutron stars, the resulting black hole should follow a neutron star mass distribution. And we know from our supernova modeling and from our astrophysical understanding is that the neutron star masses should basically follow what is shown right here. They should be peaked around 1.5. So if you detect a signal that is higher, just doing a simple comparison by eye or a more complex statistical analysis of more data, you can just make already a powerful statement that it will be difficult to account with any kind of dark matter interaction with neutron stars for solar mass black holes bigger than 1.5 solar mass. Thank you.
Okay, thank you. So we have another question still for Anirban and Jeffrey. And the question is, have you thought about the impact of steroids, neutrinos, I guess, in your studies? So, well, this time, Jeffrey, you go first, and then Anirban.
Yes, thank you for the question. We did, and in each of our plots, both for the effect on the diffuse supernova neutrino background and the high energy astrophysical neutrinos at IceCube, we plotted two different things. One was a nu tau self-interaction. Yeah, thank you, right there. So this orange line is tau neutrinos self-interacting. And then this light blue line is same thing, but with an EV scale sterile neutrino that mixes with the active neutrinos, having a self-interaction. So in this, this blue curve, that would have all of the sort of standard model neutrinos not self-interacting and only in this sterile sector. So we did consider that, as you can see, and it has a very similar effect.
Anirban?
Yeah, thanks. Yes, we also considered the impact of sterile neutrino, but before going into that, I want to say one thing. There is, it's not a very easy task to include massive sterile neutrino in a cosmological code, because in that case you have to consider its mass, and you have to go to massive neutrinos with probably mixing with other active neutrinos, and that becomes very complicated. Even if you start with some interaction, let's say only in the sterile sector, but through mixing, that interaction can leak into other active states, and you end up with a very, very complicated coupling matrix. That's, I mean, it's not impossible, but it's very difficult, and it's one of our future direction to go. But one thing that we did, which is not included in the talk, but it's in a paper. We considered a case where only one active neutrino, active neutrino flavor is interacting, and we also add ineffective as a free parameter in our analysis. But even if even in that case, we don't get a very, like, we can't really reconcile the values of Hubble from CMB and from the Schur's analysis. For example, I'm looking at my paper, the value of Hubble with an analysis with Planck temperature and polarization and CMB lensing data, we get a Hubble value of about 69 and an upper limit of N effective 3.4 roughly. So that's really in the middle between the CMB value and the Schur's value. So in this case it doesn't really solve the Hubble tension completely.
Okay, thank you. And another question for Sergio. So in your talk, you show a plot in which you present a constraint on the annihilation cross-section for the dark matter. And you show this one. And you show that ARCA, 1 year can do better than Antares 11 year. And I was wondering if you have any hint of what would be the constraints for, I don't know, 10 years of ARCA. So would you gain other orders of magnitudes? I guess so, but.
Yeah, well, so can you hear me?
Yeah.
Okay, sorry. Yeah, so so the expectation is that we gain, right, about factor 10 with ARCA in 1 year. And this is mainly because of the size of the detector, because here we are accounting for 115 strings. And in the case of Antares, we have 12 strings. So we have a factor 100 more lines. Well, here we are comparing factor 10 less for time. So you can rescale these numbers, but well, the point is that also the other detectors will be taking data. So you can wait for 5 years, but also the other limits will be pushing down, okay, and excluding. So this is indeed just to give you a taste of the kind of power that you can reach with these kind of devices. And also, well, we are doing an indirect search for dark matter. These kind of telescopes are sensitive to this energy range, so high, let's say high WIN masses. And the fact is that we don't really know, as you know, we don't really know where that dark matter can be. So which is the mass of the real mass. So maybe we are just trying to hunt something in the wrong region. We don't know. But the fact is that if dark matter is WIMP and is produced in the galactic center in the sun, at these energies, we will see it. Yeah.
Okay, thank you. And I think we have time for one last quick question for Maria Cristina. So in your talk, you were also talking about these simulations of core collapse supernova. And I wanted to ask you about them and about the dimensionality of these simulations. So are these like a 3D simulations or the dimensionality is less?
You're talking in general or when we do flavor evolution?
Yeah, for instance, when you do flavor evolution.
Okay, so let me first say in general. In general, in fact, it's only very recent, just a few years, that different groups around the world are running three-dimensional simulations for different progenitors. So the dimensionality has increased a lot in the last years, and now it's a question of CPU time to really track the full evolution of these three-dimensional simulations. So the simulations on the astrophysics side are very sophisticated. For the flavor evolution studies, we usually make simplifications because otherwise the problem becomes too complex. It is indeed a 7-dimensional problem. And therefore, a lot of studies, in particular for the very first bulb model, after the discovery that self-interactions are very significant in this dense environment, we have done lots of studies by considering spherical symmetry, isotropic emission of the neutrinos. But nowadays we are increasing, the complexity of the last decade we have increased a lot the complexity of this model. In binary neutron star mergers, where also you have flavor conversion and lots of neutrinos with astrophysical conditions similar to Kokolov supernovae, you do have to break the spherical symmetry. So the complexity of neutrino flavor evolution in binary neutron star merger has to be two-dimensional from the start. So it's much more complex.
Okay, thank you. So I would like to thank all the panelists, and if the attendees have more questions,